All right, so this one is called unfamiliar functions. So ones that you wouldn't necessarily know what they're going to look like when you graph them, that aren't polynomials as well. So sometimes drawing familiar graphs requires fewer ordered pairs because you know the shape is already known reasonably well. For example, you know a quadratic is going to look like a parabola. Unfamiliar functions are more tedious since you're not really sure what the final shape's going to be. You definitely are going to have to plot points or use your graphing calculator or maybe both. And to be successful in the exam, you do need to be able to do both. So a couple examples of some unfamiliar functions would be the logarithmic function, a rational function, which we did rational functions in the previous section, but those were all pretty predictable. These are unpredictable. Absolute value functions, those are actually predictable if it's just some kind of basic absolute value. We'll look at those in a minute. Greatest integer, we're not going to talk a ton about that, but there is some more information in your book about that one. And then a piecewise function. A piecewise function can look like anything. It's pieces of individual functions. Okay. So first, absolute value function. This one does have a parent function of the absolute value of x, and that's over there to the right. You can transform this graph just like you would any other ones. So for example, looking at A here, we have the absolute value of x minus 3. Now that's as opposed to the absolute value of x plus 2. If you have something on the outside, that's going to move it vertically. So this graph's going to go down 3. All the points are going to go down 3. For B, because that plus 2 is on the inside, that's a horizontal shift. That's going to go left 2. So you can literally take these points and just shift them for these two problems here. So for A, I'm going to shift all of those points down 3. So 0, 0 is going to go down 1, 2, 3. 1, 1, 1, 2, 3. And it's also symmetric. So really, I don't have to move all the points because once I move 1, 2, 3, like one of the ones on the right, I know where the one on the left is going to be. And then we'll use one more here. 3, 3, 1, 2, 3 would go down 1, 2, 3. Okay, and I could continue doing that all day. That's going to be the absolute value of x minus 3. On the left here, or on the right, this graph is moving left. So the 0, 0 is going to move left 2. Let's say the negative 1, 1 is going to move left 2. To be symmetric, we're also going to have a point there. I'm just going to move this part left. Negative 2, 2, moving left. And then 1, 2, 3, 1, 2, 3 moves left. Okay, and then again, we've got that symmetry on the other side. Okay. Now let me show you how you would put that into the calculator. So we go to our y equals, get rid of this. Okay, you can get to the absolute value two different ways. It's the very first thing in your catalog. So if you hit second and the 0 button, there's your absolute value. Or we can go to math. Either way, make sure you're in your y equals, okay? Go to math, and there's lots of useful things in math. If you go over just 1, that's where your absolute value is. Now, I have a newer calculator, so mine looks like an absolute value. If yours does not, if it says ABS parenthesis, just make sure that you put anything that's in the absolute value in that parenthesis and then close it. Okay, so I'm going to hit graph. And that's comparing it to the graph that you can see over there on the left side of the screen. Looks exactly the same. You need to plot some points. There's your table. Okay, there you go. Now the other one, I want to put something inside the absolute value here. So that's going to be the plus 2. Come out here and get rid of this. And graph. This graph moves to the left. And there you go. Now, the next function is called the greatest integer function. And this function rounds, it rounds down, which seems weird because it's called greatest integer, but it rounds down to the greatest integer that is less than or equal to that number. It's also called a step function. Now, page 149 in the margin gives you more information about this function on graphing it especially. I want you to know how to evaluate it though. So think about a number line as we do this. We'll kind of draw this as we go. So if I'm doing the greatest integer of 4.6, kind of just looking at the numbers I have here, I don't need to do the -7. You'll see why here in a minute. So we'll go from -3, -2, -1, 0, 1, 2, 3, 4, 5. Okay, so 4.6 would be somewhere in here. So the greatest integer says that you're going to go to the greatest integer that is less than or equal to x. So an integer is a whole number. It doesn't have a decimal with it. So the greatest integer that is less than or equal to x would be 4. 5 is not less than x, so 4 is the answer. Okay, I'm going down underneath that, 5.999. Okay, I don't have enough space on my number line for that one, but that's going to be about like right here. Okay, so 6 is too big. It has to be the greatest integer that is less than. So that would be 5. Now, if you do -0.6, -0.6 would be somewhere, actually, somewhere maybe more down there. So the greatest integer that is less than that would be -1. Going underneath that, -2.9 would be like right there. Greatest integer less than that, -3. Now 2, greatest integer less than or equal to x is 2. 2 is an integer. I couldn't do that on the last ones because those were not integers. They had decimals with them. -7 would be -7. Okay. Now just to show you real quick how that looks when you graph it, okay, and how you do that, it's in your book. See if I can remember this actually. We go to y equals here, we get rid of this, and we're going to go to math and over to number, and we're going to go down to number 5. That's going to be my greatest integer. We're going to type in the parenthesis here, what I'm doing the greatest integer of. You can do it of some kind of a function. It can be x plus 1. You can take this greatest integer times something. You can add something on, just like you can with an absolute value. You hit graph here, and you'll see why it's called a step function. Now, some graphs actually connect the steps up and down, but it's just these narrow lines here, horizontal lines. So what this means is all the way, say, along this line, if I plug any of these decimals in here between 2 and 3, all of those are going to give me x values of, I'm sorry, that's between 3 and 4. This is 3, this is 4. They're all going to give me y values of 3 because I'm always running them down. But as soon as I get super close to 4, I'm going to bump up. Now, what you cannot see on these graphs is that each one of these steps has an open circle on the right-hand side because as soon as I get to 4, I'm going to jump up to another step. And then same thing as you go along. I highly doubt you're going to have to graph one of those, but it was in your book, so I wanted to talk about it. Okay, next part is a piecewise function. Now, I'm doing pieces here that are lines, but the pieces could be anything. Essentially, this is really big in application because this would have to do with some kind of utility plan for a certain period of time. The utility is this equation, but then for another period of time, the utility is this other equation. So in this case, this graph is good when x is less than or equal to 1, to -1. This graph is good when x is greater than or equal to -1. So all of these points right here are points that are on that first piece of the graph. And then these are all graphs that are on the second piece of the graph. Now, one thing that confuses people on this is, well, why is this on the blue graph? Because it says less than -1. That's because your graph can be super close to -1. So you're plotting these points here, okay? And I got all these points just by plugging the numbers into that blue equation. Okay, and then I did this one right here and did an open circle. That's because -1 is not actually on that graph. But -1.5 is, and -1.1 is. So how you represent that on the graph is by going ahead and plugging in -1, even though it's not part of the graph, and you put an open circle there. And then I go on to the other graph. Definitely need to graph the -1. And then there's the 0 and the 1 and the 2. And there's actually more here that aren't in the chart there. Now, again, you could have one piece that is a line. You could have another piece that's a parabola. You can have more than two pieces. It just totally depends on the graph. You can put this in the calculator, but you have to put it in one piece at a time. And realize that when you plug, say, this into the calculator, you're really just plugging in the 2x plus 4, and it's going to give you all of these numbers. You can only look at the numbers that are -1 and less. Same thing when you do the other one here. You can plug -x plus 3 into the calculator, but you cannot look at any of those x values because they're not included. Okay, the last one. This is definitely an unfamiliar function. I really have no idea what this is going to look like. Let's type this in here. So we have, now you could do this by hand if you needed to. You would just make a table like you would anything else. But let's go ahead and just put it in the calculator here. So that's going to be 3x e, and actually I didn't mean to use that e. It doesn't really matter, but there's an e above the natural log button that already pops up an exponent. You can use the e that's over here, okay? Totally up to you. Okay, so I'm going to hit graph and let's see what happens here. Okay, so what it looks like happened is the graph was down here, and then it kind of dipped down, and then it went back up. So let's find some numbers here to put in. So go to our table. Okay, so those numbers are getting smaller and smaller. We don't need to worry about those. And then the numbers kind of get big. So I'm going to write some numbers over here. Hold on a second. There we go. Okay, so we'll say -3 is -0.448. That's about -0.5. We've got -1 is essentially -1. We've got 0, 0. We've got 1, 8.15. And then 2 is off the charts. Okay, so let's see what we can do here. So we've got -3, 1, 2, 3 is about 0.5. -1 is about -1. We've got 0, 0. We've got 1, 8-ish. And then 2, again, is off the charts. So we could change the window for this, but I'm just going to go with it the way we have here. So the graph is kind of doing this, and then coming down here, and then shooting straight up. Okay. All right. Last little comment here is that if you have a rational function, make sure that you are graphing those asymptotes. The vertical asymptote, you can set that denominator equal to 0, and then the horizontal asymptote, which I don't have down here, but the horizontal asymptote can be found, well, it's on your paper, by plugging in large values of x. Now again, some of this might be still unpredictable. You do have things that are called slant asymptotes. If it looks like that you kind of have a diagonal line that kind of seems to split the graph, that's what that's called. You can have more than one vertical asymptote, and it is possible for you to have a graph cross a horizontal asymptote. Normally that doesn't happen, but sometimes you can have something that looks like here's an asymptote, here's an asymptote, here's an asymptote, and you have a graph that does this, that does this, and then in the middle, the graph does that. So the right-hand sides take that asymptote into consideration, but the middle does not.